Hello, welcome to software testing methodology. So today I am going to discuss the topic is good and bad state graphs. So what is meant by state graph? I already discussed in the previous chapter. So now we'll see what is good and what is bad in the state graph. So first one is good state graph. So the state graph which can be good and which follows all the principles, it is known as good state graphs. So whatever the principles we are to define in the state graph, that principles should be followed. If the flow graph should follow that principle, if the graph should follow that type of all principles, it is known as a good state graphs. So the number of states in the state graph must be same as the product of possible number of factors. So whatever the states can be defined in the state graph must be as same as the product of possible number of factors. So for every unique combination of state and input, there should be one transaction specified. So from one state to the another state, if the transaction is specified, that transaction should be only one transaction, then it is said to be good state graph. For every transaction, there is at least one sensible output. How many number of outputs is there? No problem, it was, but at least one sensible output must be there for the state graph. Then it is said to be good state graph. So next, coming to the bad state graph. How we can call it is a bad state graph. The state graph which doesn't follow any principles. It doesn't said to be good state graph. It is a bad state graph. There are some cases to show the bad state graph. These three are leads to bad state graph whenever see these two nodes with there is no transition between these 1 and 2, like so see this 1 defines a comma b and 2 defines 1 comma 2, but there is no transition. So this is a if there is no transition between these two, then it can't say it is a state graph. There is no transition, so that's why it is called as a bad state graph. Here both states 1 and 2 are not reachable, so there no path between them, so it is a totally bad state graph. This leads to one bad state graph. And second one is nothing but, see this, there is a transition, but here one performs the same A link and 2 now performs the same A link. Then if input B at state 2, if input B is received at state 2, the path is undefined. Such type of case is known as a bad state graph. And here there is a transition between one node and two node, and there is a link as different links like A comma B, but here there is a two transitions going on between two states, so it leads to be confusion. So this is also said to be bad state graph. So all these are the conditions which results, which rises, which defines the bad state graphs. So this is the bad state graph. Next, coming to the comparison, how the good and bad state graph will be defined. So see this all 5 comparisons. First one, if the elements of the state graph, that is nothing but inputs, transitions, outputs, what we discussed in the previous chapters, are clearly specified and they are easily understandable and they are said to be good state graph. If those elements are not understood and not specified, it is said to be bad state graph. So coming to the second one, in a good state graph, every state should have a sequence of inputs that drives the system to the starting state. So in the bad state graph, there is no sequence, there is a randomly accessing. So there is no initial state, this is not to initial state. So all this comes under the bad state graph. So that is the second comparison. So third comparison is nothing but there should be only one transition specified for one state and input combination. But in the bad state graph, there is more transitions will be specified. That leads to the confusion states. So that is said to be also one of the comparison between good and bad state graph. Next, fourth one, the fourth comparison, there would be only one output for every transition because unique output gives clarity. Otherwise, it leads to confusion. Same here in the bad state graph, there is no clarity. There is more than one output transition. This leads to improper state graph. Then it is called as a bad state graph, and this is one of the comparisons. Next one, here bugs are less and they are easy to find. But in the bad state graph, bugs are very large bugs will be defined. So that it leads to the bad state graph and is difficult to find. And this is about the comparison between good and bad state graphs. Next, coming to the bugs. What are the bugs rises in the state graph? There are two ways the bugs will be raised. One is state bugs and second one is transition bugs. State bugs means the bugs which occurs on the states is known as the state bugs, and the bugs which occurs on the transitions, nothing but state changing behavior of a system which changes from one state to the another state. So if the bugs are raised, the problems are raised, that is known as a transition bug. So what are the reasons of which state bugs are arise, or the number of states, possible states, equivalent states. These are all the common bugs, common problems rises in the states. So what defining the number of states, if there is any impossible state, if there is any equivalent state, this cause to state bugs. So what is the number of states? The number of states in the state graph can be considered as the number of states that are required to identify the behavior of a system. So every state graph is very important to state testing. So mainly this number of states, how many states defines in the state graph. If there is number of states, how the behavior of system is to be. All can be identified, are required to identify. This causes, by identifying this number of states, this causes state bugs. Every state of the graph is very important to the state testing. So it is essential to find the number of states. It is very important to find the number of states. By finding this type of number of states, this causes the state bugs. So there the state bugs will be occur. The number of states can be identified by finding all the factors of the state, finding all the possible values of each factor. To be find out the factor, to be finding all the possible ways that reaching the factor, whatever we have find. In this, the number of states will be identified. When the number of states identified, the bugs also will be identified. So that is one of the case which defines number of states. Next one, impossible states. The name itself tells impossible. So this leads to the bugs. There can be some combinations of factors that may appear to be impossible. If these factors are included, they lead to impossible states. So if the impossible states doesn't have any meaning in the systems, as the impossible states are the one which not possible to occur. So this is about the impossible states. Next, coming to the example of impossible states. So direction, gear. So here I am taking the car. Car is the example. So here car has direction as a forward, reverse and stop. Gears is nothing but reverse, neutral, 1, 2, 3, 4, 5. These are all the gears. And engine operation is running or stop. Engine condition is good or bad, nothing but faulty. So here direction takes 3 factors, gear takes 7 factors, engine operation takes 2 factors, and engine condition takes 2 factors. Total 84 states will be defined. So this is the impossible states which defines number of states in the graph. This causes some of the bugs raises as state bugs. So nothing but equivalent state. The name itself tells sequence of inputs from one state generates exactly the same sequence of outputs for other state. So it leads to the equivalent states. So in this equivalent state, it takes, if we have 84 states, it takes some time. There is a sequence missing of sequence will be done. So it leads to the state bugs. When both the states produce same output, then only one state would be enough instead of 2 states. So that defines the equivalent state here. So routine, here we are taking the 4 aspects as the routine aspects. Routine 1, 2, 3 and 4, and starting state S, and another states, rest of all states, inner states P, Q, R. So I, J is the link represent transitions which starting state to the P and the starting state to the Q. So this is the example of equivalent state. Here routine 1 is the one input we are taken, and routine 4 is also one input we have to define. Then it is said to be equivalent state. So whenever the equivalent state defines, it leads to best state graph. But if there is any equivalent state rises some bugs also in some cases, then it is called as state bugs. So next, coming to the transition bugs. What are the transition bugs? So transition bugs are mainly caused due to unspecified and contradictory transitions, unreachable states, dead states. So what is meant by unspecified and contradictory? So the name itself tells specification is not done, nothing but unspecified. So for every state input combination, there should be a transition specified. I already told you in the previous slide, like A, B, there is no transition between A and B. So that is nothing but unspecified. If the transitions are not specified, then the bugs can occur due to unspecified transition between the states. This leads to the transition bug. Next, what is meant by unreachable states? If there is some state which no input sequence, So no transition also can defines, name itself tells not reaching, nothing but unreachable. Then it is known as unreachable states. There are transitions from unreachable states are incorrect transitions. So dead states, killed. Dead states is such a state if it is entered once, that state cannot be left. Some killed state or performing dead state. Deadlock will define the deadlock or dead condition. All can be defined as a dead state as it leads to the transition, but in there the inputs cannot be processed from the dead states. So this is the example for dead state graph. See here B, A will be dead, A comma B. So A will be transition and 2 reaches the A, but B is a dead state. So this leads to the dead state graph. Next, what is meant by output errors? So whenever the output is receiving at the end side, there the bugs will be raised, there the problems will be raised, there the errors will be raised. The output of the transition could be wrong even if all the state transitions and inputs are correct. Then there are no dead or unreachable states. So that is called output error. And the reason for wrong output would be incorrect call to the routine that should be executed for output. This is a minor bug. So this is a minor bug. So no problem about this bug. And it is also leads to the transition bug. Next, encoding bug. The process of converting, encoding is nothing but conversion plain. Generally, encryption means conversion of plain text to ciphertext. Decryption means ciphertext to plain text. So encoding also converting of the code inputs, transition and outputs of the states in order to obtain the secure process of FSM. Nothing but final state machine is known as the encoding, and it is the essential process, nothing but important process in state testing or transition testing. And whenever this conversion is going on, if the problem rises, it is known as the encoding bugs. Encoding is done in both in explicit and implicit phase. Internally and externally, the encoding will be done. So this is about state bugs and transition bugs and good and bad state graph. How can you say good and bad state graph? How can the bugs will be rises, where the bugs will be rises, and it is known as a state bug. If the bugs rises in the transitions, it is known as a transition bug. So hope you all understand about these state bugs and transition bugs and good and bad state graph. So thank you very much.